Sustainable drainage systems. Welcome to this presentation on sustainable urban drainage systems, very often simply referred to as SUDS. My name is Ian Fraser and I will be giving a brief overview of SUDS to help explain why it has been developed and explain the process of designing a SUDS system. I hope you enjoy my presentation. This presentation will cover the following topics. In order to appreciate why sustainable drainage systems are used for surface water drainage, it helps to understand how drainage developed throughout time. So the first section gives a brief history of drainage. Conventional drainage systems have limitations which SUDS attempts to rectify. So the next section of the talk will highlight some of these limitations. During the last 100 years, it has been realised how important our natural resources are, and especially water. Over the last few years, legislation has been introduced specifically to protect the water environment, so an overview of this legislation is discussed next. Best management practice, or SUDS, has advantages over conventional drainage systems, so these will be highlighted in the next section. The following two sections show an overview of the process of designing a SUDS system and selecting a suitable SUDS device. And the final section of the presentation shows a few images of SUDS devices in use and also highlights some of the disadvantages of SUDS. The presentation will take approximately 30 minutes to complete. Drainage throughout time. Drainage systems are probably as old as mankind. It is not inconceivable that the earliest cave dwellers would have dug channels in the cave floor to direct water runoff from the cave roof away from the living and sleeping areas. The earliest drainage systems in Scotland date back 3000 years BC. Basic toilets within recesses of the stone huts in Orkney at Skara Brae had drained outlets, and there were simple drainage systems under or outside the buildings. The ancient Romans had water and drainage systems as well. They erected bathhouses, surface water and sewage systems, including aqueducts for transporting the water, similar to the one shown in this photograph taken outside Rome. The earliest medieval sewers in Britain were basically open ditches, sloped to convey foul water, surface water and any other waste to the nearest watercourse or the sea. By the early 1700s, nearly every home in towns and cities like London had privies with a cesspit beneath it. All the human waste was collected in these cesspits, which smelled terrible. These cesspits had to be dug out and the contents removed regularly. Rainwater from the roofs and the roads continues to be drained into the nearest watercourse by open ditches. By the 19th century, the populations of the towns and cities increased significantly. The census of 1851 recorded half the population of Britain living in towns. In the early 19th century, the more affluent households in cities and towns like London were installing water closets in place of the privies. With the extra water being used to flush the water closets, the old cesspits were no longer suitable, but the foul water from the water closets had to be discharged somewhere. By this time, most of the open ditches for rainwater had also been replaced by drainage pipes, so the surface water drainage pipes were used to receive the foul water. This is probably the start of the combined sewer systems of the Victorian era. In London, the water from the combined sewers discharged into the River Thames. This caused a crisis in 1858 when the smell of the River Thames became so overpowering that the curtains in the House of Commons had to be soaked in chloride of lime to protect the noses of the sensitive MPs. Cholera epidemics in the 1830s, 1840s and again in the 1850s awakened the need for a solution. Between 1853 and 1854, a London doctor, John Snow, identified the cholera field in London was caused by sewage-contaminated water from the River Thames. This eventually brought about the introduction of water treatment systems for sewage. The limitations of conventional drainage. Conventional drainage continued to be used throughout the 20th century for surface water. Some was combined with foul water and treated in water treatment plants, but most surface water was simply discharged into the nearest watercourse. The original objective of surface water drainage was to remove water from the streets and the houses. During severe weather conditions, conventional drainage only has limited capacity to store excess water. As the amount of water increases, the pipework reaches capacity. Eventually it overflows, causing flooding. No consideration was given to the pollution that might be caused. Water runoff can pick up various polluting substances, such as animal feces, debris from human activity, airborne pollutants, and hydrocarbons from vehicle emissions. These are transported by the water into the watercourse, causing pollution. If the watercourse is a source of drinking water, this could cause health problems, including diseases such as cholera. This waste transported into the rivers might be rich in nutrients, triggering eutrophic conditions in fresh water. Eutrophic water encourages the increase of growth of algal blooms and microorganisms. Both can cause reduced dissolved oxygen levels in the water, leading to reduced biodiversity. Conventional drainage systems have no method of removing these pollutants before they reach the natural environment. Water legislation. The mid-20th century saw the introduction of legislation specifically designed to clean up the water environment and reduce pollution levels. The table in this slide shows some of the legislation that has been introduced since the 1960s in order to clean up the natural water environment. One of the most significant in recent years has been the European Water Framework Directive. This has been transposed into Scots law by the Water Environment and Water Services Scotland Act 2003 and is implemented using the Water Environment Controlled Activities Scotland regulations, very often simply referred to as CAR. The regulations first came into force in 2005 but have now been reviewed and updated in 2011. The Controlled Activities Regulations specify the level of authorization that is needed when carrying out activities in or near a watercourse that has the potential to cause pollution. These activities include discharging water, abstracting water, diverting a natural watercourse, and constructing dams, weirs and other engineering works in or near the watercourse. The advantages of SUDs. To improve the water quality and reduce pollution in the natural environment, the surface water drainage management and source control techniques have been developed. These are sometimes referred to as best management practices, or sometimes by the acronym BMP. More recently, these have been called Sustainable Urban Drainage Systems, or by the acronym SUDS. As these techniques are now used both in urban and rural locations, the word urban is very often dropped from the name. SUDs use natural processes to attenuate the excess runoff and remove pollutants from the water. These natural processes include allowing water to infiltrate through a SUDS device into the ground. Many SUDS devices provide filtration through gravel or grass, which helps remove pollutants. Some SUDS devices retain water on the surface, allowing evaporation and evapotranspiration to take place. Artificial ponds are also used to contain excess runoff and allow heavier pollutants to settle out of the water. The concept of SUDS is epitomized by the quality, quantity and amenity triangle, which is shown in this slide. Designing a SUDS system. The process of designing SUDS consists of information gathering, estimation, and finally determining what will happen to the water. The catchment area is the first piece of information that is needed, as this will determine the amount of water that the SUDS devices need to deal with. The catchment can be determined from ordnance survey maps and land acquisition plans, etc. This area is normally the development site, but the surrounding area may also need to be considered. If the local topography is likely to introduce runoff onto the site from surrounding higher land, then this will also need to be considered. The impermeable area is usually determined by adding up the total road surface, footpaths, building roofs, driveways, parking areas and any other hard standing intended for the developed site. If the development includes permeable design for car parking, footpaths, etc., this needs to be considered and not included as part of the impermeable area. The annual rainfall is based on the historical rainfall records taken over a 30-year period for the area under investigation. This information is available in the form of meteorological maps provided by Wallingford Hydro Solutions and covers the period from 1941 through to 1970. The Flood Estimation Handbook and related software is available from the Centre of Ecology and Hydrology and provides rainfall data from between 1971 and the year 2000. The ground conditions can be determined from actual ground investigation on the site, and this will determine the ground percolation rate. Wallingford Hydro Solutions also produce soil survey maps giving details of the winter rainfall acceptance potential, from which the soil index can be calculated. The site topography, such as slope and any nearby watercourses, can be attained either from the site visit or from relevant ordnance survey maps. Other useful sources of information are Google online maps and in some cases historical maps of the area. Not all the information can be gathered from the site visit or published material. As already mentioned, the soil index needs to be calculated from the winter rainfall acceptance potential of the area, and there are other pieces of information that need to be calculated. During an extreme rainfall event, there will be more water generated by the storm than can infiltrate into the ground. The excess water will either run off from the site into the nearest watercourse or may cause flooding either on the site or off the site. Developing a site will increase the impermeable surfaces, and this will reduce the permeable area that the water can infiltrate into. A developed site will therefore have a higher water runoff during extreme rainfall than the undeveloped site. It is therefore necessary to calculate the runoff flow likely during a rainfall event on the undeveloped site. This is known as the pre-development flow. Once the pre-development flow is known, it is then possible to calculate the amount of runoff from the site after the development is complete. This is the post-development flow. The final piece of information required will be the volume of water that will run off from the site during the rainfall event. This will be determined by the runoff flow rate and the duration of the storm. This is needed to correctly size the SUDS device. There are a number of different methods of calculating the runoff flow. These include a rule of thumb method, Poots and Cochrane method based on the UK Flood Studies report, mean annual flow, the modified rational method from the Wallingford procedure, and finally the method in the Institute of Hydrology report number 124. The next important consideration when designing a SUD system is what is going to happen to the water. If the ground percolation rate is suitable, then once the water has been cleaned through a suitable SUDS device, it could be allowed to infiltrate naturally into the ground. If the ground has poor percolation conditions, then other options may have to be considered. Can the water be discharged into a nearby watercourse? If it can, you may have to check with the Scottish Environment Protection Agency, as any discharge into natural water is considered a controlled activity under the Water Environment Controlled Activities Scotland regulations, although a small surface water discharge might only need to comply with the general binding rules of the regulations. If there is a public drainage system nearby, then the SUDS discharge may be able to connect straight into this, but consultation will be required with Scottish Water before this can be done. As already mentioned, the meteorological data is available from a set of Wallingford rainfall maps. These maps, which include the entire British Isles, include the Standard Annual Average Rainfall, or SAR, which is expressed as the total rain falling in a year and reflects the wetness of the area. Two other maps show the 5-year return period rainfall with a duration of 60 minutes and a 5-year return period rainfall with a duration of 2 days. Another map indicates the ratio of rainfall amounts. This is the ratio of a 5-year 60-minute rainfall against the 5-year 2-day rainfall and reflects the viability of rainfall at a location. The final map in the set is the Soil Survey map. This provides winter rain acceptance potential, or RAP, which is given as 5 soil types representing the ability of soil or rock to allow infiltration in the winter. The 5 soil classes range from sand to heavy clay or bare rock. The modified rational method is one of a number of different methods to work out the rainfall intensity, maximum flow and volume for a specific development site during a specific rainfall return period. The modified rational method is suitable for small developments. QP is the peak discharge expressed as litres per second. CV is a dimensionless coefficient representing the volumetric runoff and the percentage of runoff divided by 100. I is the average rainfall intensity during the time of concentration and is usually given in millimetres per hour. A is the contributing catchment area and is given in hectares. Selecting a suitable SUDS. SUDS can take the form of both procedures and devices. Procedures can include safe disposal of pollutants, detailed instructions on unloading oils and chemicals in a factory, asking dog owners to collect their pet feces for safe disposal. But irrespective of the type of development, residential or industrial, prevention should always be considered first. Containment should be considered on industrial sites to prevent chemicals or hydrocarbons polluting the environment. To select suitable SUDS devices, consideration should be given to where the water can be disposed of. Can it infiltrate into the ground? Can it discharge into a nearby watercourse? How big is the development? Will one SUDS device be sufficient, or will several devices be necessary? Will source control be sufficient, or will site control also be necessary? How much space will be available for SUDS? Does the slope of the ground eliminate certain types of SUDS design? Ponds, wetlands and detention basins will need a large amount of space. Other important considerations with SUDS devices are the risks to health. Bodies of water such as ponds can attract small children, so consideration needs to be given to reducing these types of hazards. Types of SUDS device will often depend on the level of treatment, ground conditions, amount of water to be treated, and the size of the site. Small residential sites will only normally require the first level of treatment, so filter drains, filter strips or swales might be adequate for source control. Large developments may need both source and site controls, so detention basins and ponds might be required for the site control. Industrial sites might need 3 levels of control. These could consist of procedures to reduce contamination as mentioned previously, filter drains and swales to treat and transport the water into a level 2 treatment such as a pond or a wetland area. Filter strips and swales might be more appropriate to collect sheet flow from a stretch of road, while a permeable surface might be more appropriate for a large car parking area. Well-designed and planned SUDS systems will fulfill the concepts of the SUDS triangle. However, there are disadvantages with SUDS systems. The first is poor design, which can eliminate the efficiency and provide adequate treatment for attenuation. Poor design can also reduce the amenity value. A regular shaped deep ditch or pool with steep sides is unlikely to enhance the appearance of a development site or attract wildlife. Poorly located and badly designed SUDS devices will attract rubbish, again reducing the efficiency and amenity value. Old bicycle frames, shopping trolleys lining a detention basin or pond will detract from the amenity value. SUDS are designed to replicate natural processes, but that does not mean that they are maintenance free. Ongoing maintenance of any SUDS device needs to be considered at an early stage in the design process. Poorly maintained SUDS devices will become overgrown, become choked with vegetation or other debris. Heavy rainfall can cause erosion or expose filter drain membranes. Sediment build-up over time can block inlets, drainage channels and reduce storage capacity. These are some typical urban SUDS devices in operation. The first image on the left appears to be a retention basin or possibly a wet detention basin, as it appears to have a wet area. The surface water runoff from the housing estate in the background is transported through a conventional piping system into the basin. After attenuation and treatment, the surface water is discharged into a small stream. The image at the top right shows a filter strip alongside a public road. Surface water from the footway can flow across the grass swale and enter the filter strip. Due to the curb, the excess surface water from the road would probably enter conventional gullies before finding its way into the filter strip. The image on the bottom right appears to be a stream that was probably on the site before it was developed. In this case, the banks have been sloped and planted with grass to provide both improved visual appearance and maintain the land drainage into the stream. This image shows a larger picture of the retention basin from the previous slide when it was first constructed. The construction of the housing estate in the background, as you can see, is still taking place. 5 years later, the vegetation around the wet pond area has been allowed to grow, creating a miniature wetland pond area. An interesting point is that the only barrier between the SUDS device and the public road is a hedge to protect the inlet culvert. The rest of the site is accessible from the public road. Referring back to the slide on considerations when designing a SUDS system, some thoughts need to be given to safety and health risks. The photograph was taken in the direction of the blue arrow that shows a small child's toy dumper truck partly submerged. This suggests that children are playing near the wet pond area, and this could be a health risk. It's also interesting to note that there are beer cans that have been dumped into the pond. This presentation has covered a brief history of drainage from the Stone Age until the present. It has highlighted that conventional drainage was only designed to remove water, with no method of treatment and only limited capacity for storage. This resulted in health risks, reduced biodiversity and increased flood risk. Over the last few years, legislation has been introduced specifically to protect the water environment, in particular the Water Framework Directive, the Water Environment and Water Services Scotland Act, which has been implemented using the Water Environment Controlled Activities Scotland regulations. Best Management Practice, or SUDS, can be used to transport surface water, provide a method of water treatment and provide attenuation and improve amenity. The SUDS triangle. To design a SUDS system, and the catchment area, impermeable area, annual rainfall, ground conditions and nearest watercourse need to be obtained. Pre-development and post-development flow can then be calculated along with the volume of water that is generated. Rainfall data is available using the Wallingford rainfall maps. The modified rational method is just one method that can be used to attain the peak flow. Selection of a suitable SUDS device will depend on the size of development, ground conditions, amount of space available and the location of the watercourse. Poor design, lack of maintenance and being used as a rubbish dump are some of the disadvantages of SUDS. Thank you for listening to this presentation. If you need further information on help with surface water problems, then please do not hesitate to get in touch.